Hello and welcome to Lecture 7 for Unit 3 of Intro to Logic. We're going through derivations and predicate logic. We've got our four rules: existential in and existential out, universal out, and universal derivation. That's actually all we need to do any derivation that's valid in predicate logic. But just like it makes sense to add negation rules to make our lives a little easier when we have lines whose main operator is negation, it makes sense to have negation rules for the quantifiers too. So when you have a negation as the main operator and it's applied to a quantifier, you can apply one of these two rules. So let's look at the unofficial, the informal versions. If it's not true that for all x something about x, that means you get from that there is an x for which it's not true that everything is x. That should make sense. If it's not true that everything is a certain way, then something must not be that way. So look at the example, not everything is colored, therefore something is not colored. So what this does is it moves the negation from one side of the quantifier to the other, and it changes the universal quantifier to the existential quantifier, the upside down A to the backward Z. Nothing else about the statement changes. We also have non-existential out, which is just kind of the reverse of that. It's not true that something is. If it's not true, say that something is omnipotent, then everything is non-omnipotent. So not backwards Ex, something about X, you get for all X not something about X. So again, we only apply these when the negations are the main operators and they're applied to quantifiers. What you do is you move the negation to the other side of the quantifier. The upside down A changes to a backward Z, or the backward Z changes to an upside down A. So you can push a quantifier through push a negation through a quantifier if you change it to the other quantifier. But be sure to make that change. You can't go from not everything is to everything isn't, right? Okay, so let's look at some problems that use these rules. So let's look at this problem here. It's not true that there is something that's both f and g. Something is f, show that something is not g. We'll do this by direct derivation. And I'll start by applying the negation rule to line 1. So it's not true that something is. That means everything is not. So the negation moves after the quantifier. The backward z changes to an upside down a. So we get this when we apply this rule to line 1. Right? Nothing else about the statement changes. You just move the negation and change the backward z to an upside down a. It's not true that something is and everything isn't. So that's 1. The rule is not existential out, since we're applying this rule to negation of an existential statement. So now we have line 2 and line 4 to work with. You want to do existential outs before universal outs. So we'll do existential out on 2. And we get FA. Got to use a new name for existential out. But we're not using A anywhere, so we can use A. Now with universal out, we do universal out on 4, and we get not FA and GA. With universal out, you don't have to use a new name. You can use a name you're already using. Okay, so now we want to deal with line 6. So this is when the other negation rules come into play. So if they're not both true, then if the first one's true, then the second one is false. So that's the negation rule for negation of an and statement. 6, not ampersand out. Now we can do exponents with 5 and 7. We get not GA. And to get the something is not G, that's the show line. We just got that A is not G, so something is not G. So 8 existential in. All right, let's do another one. So this one we'll do a indirect derivation for the main derivation, since what we're trying to show is a negation. Right, we're trying to show not for all x, hx arrow fx. So we'll do this by indirect derivation. We'll assume that it is true that for all x, hx arrow fx. So 3 assumption, use show line to show splat. Sorry, that should be just assumption. All right, so we have a negation. So 1 and 4 are universals. We want to do existential outs before universal outs. Notice that when we do not universal out on 2, it's going to change the negated universal to an existential negation. So we get there is an x, not that. So we want to do that first because we want to do the existential out before the universal outs. So I'm going to do that first. So that's 2 not universal out. So nothing else changes. The arrow doesn't change to an and or anything like that. The negation just moves to the other side, and the upside down A changes to a backward Z. Now we want to go ahead and do existential out on that. Because we want to do existential outs early. 6 existential out. And then if it's the negated conditional, we get the first side being true and the second side being false. So that's 7 not arrow out. Okay, so now it makes sense to go back to the universals 1 and 4 and do universal out on them. So FA arrow GA, 1 universal out. We also get HA arrow FA from 4 universal out. So we want to break up line 8, get HA in a line, get not GA in a line. Now we have what we do to do modus ponens on 10. So HA arrow FA, we have HA, we get FA. So that's 10 and 11, modus ponens arrow out. And now we have what we need to do arrow out on 9, we get GA. FA arrow GA, we have FA, we get GA, so that's 9, 13 arrow out. Now we have our contradiction between 12 and 14. Splat, 12, 14, splat in. That's what we were trying to show. So we've shown this by indirect derivation as well. I can just click it, and then we'll check our derivation. There we go. So we'll do this one. So this one, what we're trying to show is an or statement. So you may remember from Unit 2, if you're trying to show an or statement, the advice is to do it by indirect derivation. We're going to assume the negation of the entire or statement, so not in parentheses for all x, not gx, or for all x, fx, or ix. That whole thing in brackets is what I'm going to assume for the indirect derivation. I did something wrong there. Oh, that should be an A. That's our assumption. And we'll show a contradiction. So what this is going to do is when we do not wedge out on 3, we get the negation of each side of 3. So we get not for all x, not gx. So that's the negation of the first side of 3. 3 not wedge out. Then we get the negation of the second side of 3. Not for all x, fx, or ix. 3 not wedge out. So now we have the negation of 2 universal statements. Those will change to existential negation. So we push the negation through the quantifier and change this to the other quantifier. So when we push the negation through the quantifier on 5, this negation comes over. There's already negation still there, so it ends up with a double negation. So the upside down A changes to a backward Z. That first negation moves to the other side, so we end up with 2 negations there. So that's 5 not universal out. We'll do the same thing to line 6. We get backwards EX not FX or IX. Okay. So now we want to do our existential outs before working with anything else. So we have 2 existential outs to do, 1 and 7, 1 and 8. You can't do existential out on 1 because the existential is not the main operator. If we want to do 1, we need to get the existential, so then we can do modus ponens to get the other side of it. But first we'll do existential outs on 7 and 8. So we get not GA from 7. We can use A since we're not using A anywhere else, so that's existential out. We'll do the same thing with 8. We get not FA or IA. I'm sorry, that should be, we need to use a new letter, so I'm going to make that a B instead of an A. Sorry about that. Do existential out, you got to use a new letter. So we're doing existential out on 8, we got to use a new letter, so we can't use A, we got to use B. We can drop off the double negatives on 9. So what we want to do with 1 is we want to get something as G. We just got that A is G, so we get that something is G by exponential in on 11. Now we have what we need to use line 1. So we get for all x, hx, and ix from 1 and 12, arrow out. Now we can do universal out on 13, but what letter do we want to change that x into? We can make it about A, we can make it about B, we can make it about C. Universal out doesn't have to be a new letter, but we have IB up there in 10, right? So it makes sense to, if we're trying to get a contradiction, something about the B's will match, more likely to give us a contradiction. So I'm going to make this x into a B in 13. Then we get IB from that, just breaking it up, but we get not IB from 10, not wedge out, right? If you have a neither nor statement, both sides are false. So now we have our splat between 15 and 16. Hopefully I didn't make any errors there. That's that one. So you see, having a negation of an or statement will change it into 2 negations. If they're quantified statements, you want to use these negation rules. All right, let's do one more. So either not everything is F, or it's not true that something is G. If there is something that's not F, then it's not true that there is something that's both H and I. So if A is G, then for everything, if it's H, then it's not I. So since this is conditional, we're going to do it by conditional derivation. We're going to assume GA, use show line to show for all x, hx, arrow, not ix. Right? That's a universal, so we'll do it by universal derivations. Remember the way universal derivation works? We just have a new show line to show an instance that uses a new name. So I'll take off the for all x in the show line, change it to a b. I can't use a because I'm already using a. HB, arrow, not IB. Now this is another conditional, so I'll do another conditional derivation. Assume HB, new show line to show not IB. Now this way I can do by direct derivation, so I will. You can also do this by indirect derivation, that would be fine. All right, so I have a lot to work with here. I have 1, 2, 4, and 7. But the main thing I'm going to be able to work with here is 4. 4 gives me that something is G, right? Since A is G, something is. That gives me, after I double negate it, the negation of the right side of 1. So that means the other side of 1 has to be true. So not for all x, fx. So that's 1 and 10, wedge out. And that'll change to an existential negation by our new rule. So 11, not universal out, gives me that. Now I want to do existential out as soon as possible. And I can't use A and I can't use B, so I'll use C, not FC. So 12, existential out. Now notice that the if part of 2 says if there is something that isn't F. We just got the C isn't F, so there is a Y, not Fy. So that's 13 existential in. Now I can do modus ponens on 2, right? So I get not there is an x, hx, and ix. Right? So that's 2 and 14 modus ponens. Now this will turn into a universal negation, not for all x, hx, and ix. Move the negation to the other side of the quantifier, changes to the other quantifier. 15, non-existential out. I can do universal out on that. Now universal out, I don't have to use a letter. I don't have to use a new letter. I can use the letter I'm already using. So I have HB. I'm trying to get not IB. And I don't have anything about h and I for A or C, so it makes sense to do it to B. So I get not HB and IB from 16 universal out. Negation of an AND statement turns into a conditional. If HB, then not IB. 17 not ampersand out. I have HB up at line 7, so I get not IB. 7 and 18. That's a long problem. Arrow out. That's what I was trying to show. So I've shown not IB. So I've shown this by conditional derivation, shown that by universal derivation, shown that by conditional derivation. All right. The next topic I want to talk about is what to do when you have multiple quantifiers right in a row. There's actually nothing to learn about this. It's just the same rules we've been talking about. There are no new rules for dealing with multiple quantifiers right in a row. But all you need to know is that you need to deal with them one at a time. If you have two quantifiers right in a row, the one on the left is more main than the one on the right. You're always working with the main operators when you're applying the rules. And when you're pushing negations through, you push the negations through one quantifier at a time. And that's really all you need to know in order to do these kinds of statements. So look at this one. It's not true that there is an x for which there is a y, of which it's not true that ryx. Show that for all x and for all y, rxy. So let's set this one up. So when you're figuring out what kind of derivation to do, you want to focus on the show line. So the show line here is a universal. If the show line's a universal, you want to do it by universal derivation. Universal derivation, there's just a new show line. You take off the main operator quantifier of that show line. You'll leave the, so that's the for all x. You take the for all x off, you'll leave the for all y there, and you only change the the x's to a new name. So only change the x's to a. So we're going to change that x to an a. We'll leave the y there. Right? We just deal with the quantifiers one at a time. Now we have a new show line. The new show line is also a universal. So we'll do this one by universal derivation as well. Sorry, when you have universal derivation, you just get a new show line. So this time we'll take off the for all y and replace the y with a new name. And we can't use a anymore, so we'll use b. And I can do this by direct derivation. So I don't have anything to work with here other than 1. So when I push the negation through 1, I push it through that first quantifier, it changes the backwards e to an upside down a. The negation is still before the second quantifier, and the second quantifier doesn't change. It's still a backwards e. Nothing else about the statement changes. So we push the negation through that first quantifier, negation goes after that quantifier, changes the backwards e to an upside down a, but everything else about the statement is the same. So that's 1, not existential out. Now the universal operator is the main quantifier. Now I'm trying to get RAB. So when I take off the for all x in 5, that second thing after the R is going to change. I want to change it to a B. So I'm trying to get something with a B there. So I take off the for all x. I'll leave the not there. I'll leave the backwards EY there. I'll leave the other not there. I'll leave the Y's the same. I'm just changing the X to a B. 5 universal out. Now the negation is the main operator of 6. I'm going to use the negation rule. I move the negation to the other side of the quantifier. The backwards E changes to an upside down A. That's the negation that moved over. The other negation is still there. So we'll end up with a double negation here. So that's what you get when you push the negation through with on 6. Again, that's not existential out. Now I can do universal out on 7. The universal is the main operator. I'll get not RAB. I'm going to change it to an A because I want to get RAB in the show line. So that's 7 universal out. Now I can get rid of that double negative. And there I have this. I've shown this, and I've shown this. All right. Okay. So let's do this next one. There is an x for which it's true that for all y, either x is f or y is g. Show that for every x, if not gx, then something is f, right? So we'll do this by universal derivation again, since we're trying to show a universal. Get a new show line for a universal statement. We're trying to show not GA, so we're only going to change the A, so leave the Y's alone. Sorry, only change the X's to A's, leave the Y's alone. That's what we want to show. Now this is a conditional, so we'll do it by conditional derivation. assume not GA, show there is a YFY. We'll do this by direct derivation. All right, so the lines we have to work with here are just 1 and 4. So we want to do existential out as soon as possible. So existential out on 1, again, to take off the backwards EX, we'll leave the for all Y the same. The X will change to a new name. I have no idea what I did there. The X will change to a new name, so we'll change the X to a B. Leave the Y alone. So that's 1 existential out. Now we do universal out on 6, so we can use an old name. So we want to change that Y to an A, so we have not GA. So FB or GA, right? 6, universal out. So then we get FB, because we have not GA. 4 and 7 wedge out. So if B is F, then something is F. There is a YFY. 8 existential N. That's what we're trying to show. Showed that. We showed that. Okay, very good. I'm actually going to skip this next problem. I think there's nothing particularly new to learn. Just remember, you take the quantifiers one at a time. If you're taking off a for all x and changing the x, leave the y's alone. Only change the x's. Right? Use a new name and do existential out, things like that. That's really all there is to do. I want to skip to this problem. This is my favorite problem, this problem down here. It's called the everyone loves a lover problem. So think of this argument in English. Everyone loves a lover. Someone loves someone. Therefore, everyone loves everyone. That's a little bit weird of an argument. It doesn't seem like it's valid, but it is, right? If everyone loves a lover and someone loves someone, well, that someone loves someone means that someone's a lover. Well, if someone's a lover, everyone's going to love that lover. That makes everyone a lover. And if everyone's a lover, everyone loves everyone. So that's really what we need to do in this argument. So let's read what that premise says. First premise, a little bit complicated. For all x, if there is a z such that lxz, then for all y, lyx. So for everything, if there is a z that it loves, then every y loves it. So if there's something that it loves, then everything loves it. So if you're a lover, everyone loves you. Everyone loves a lover. Someone loves someone, that's the premise too. There is an x, there is a y, lxy. Show that for all x and for all y, lxy. So we're going to do this by universal derivation since the main operator of the show lines are universal. So we just take out that first quantifier, leave the y there, change the x to a new name. So we're going to show for all y, lay. This is another universal, so we'll do it by another universal derivation. Just a new show line for universal derivation. Take off this quantifier, replace the variable with a new name. So I'll replace it this time with a b. Now you could do this either by direct or indirect here. I'm going to do it by direct. That's just a hint that I'll give you. If you see the everyone loves a lover problem, you have to do universal derivations. But once you get to show LAB or something like that, you can do it by direct derivation. And I should say, since this is my favorite problem, there's a good chance a problem a lot like this is going to show up at least one of the exams for Unit 3. Hint, hint, just so you know that. So the lines that we have to work with here are 1 and 2. Now, it makes sense to do existential outs first. So we do existential out on 2. And just take off the backwards EX. Leave the backwards EY alone. Change the X's to a new name. Now, we're already using A and B, so I'll have to use C. Place the X in 2 with a C. So that's 2 existential out. Now, I do existential out on 6 as well. Take off the backwards EY. Change the Y to a D. And every time you do existential out, you got to use a new name. So we'd use a new name. Now, we've gotten hit here. So what's going on in this problem? Everyone loves a lover. Somebody loves somebody. We decided to call this somebody who loves somebody C and D. So C loves D. We're trying to show that A loves B, where A and B are two completely different people. If C loves D, how do we know that A loves B? Well, since C loves D, C is a lover. That makes everyone loves C, including B, which makes B a lover, which means that A loves B. So we have to do universal out on 1. Now, universal out on 1, we have for all x. We can change that x to whatever we want. We can change it to an A, We can change it to a B, we can change it to a C, we can change it to a D. We could do all four, and if you didn't see which one is going to be useful, I would do all four, but think about what's going to change in one. Think about what's going to go before the arrow and what's going to go after the arrow. When you think about what's going to go before the arrow, you want to think about what you have. We have something with a C in that first spot. The X's are going to change. So it makes sense to change the X in 1 to a C, right? If there is a Z, such that LCZ, then for all Y, LYC. If C is a lover, everyone loves C. Well, C is the only person we know is a lover, so it makes sense to start here, but we may end up having to go back to 1 and use it again, right? Well, we know that C is a lover. There is a Z, LCZ, that comes from 7, it doesn't come from 8. 8 is the reason we want it, but C loves D, so there is a Z that C loves. Existential in on 7. That means that everyone loves C. So that's 8 and 9, arrow out. Well, if everyone loves C, that means that B does. Now, why do we care about B rather than A or C or D? We want to get that B is a lover so we can get that everyone, including A, loves B. But we just got that everyone loves C. So B loves C, LBC, 10, universal out. Now we need to use the fact that B is a lover. So if we go back to line 1 and we'll do line 1 to B. If there is a Z, LBZ, then for all Y, LYB. So it makes sense to do line 1 to B because we're trying to get LAB. When you think about what comes after the arrow, you want to think about what you're trying to get. So we're trying to get something with a B in that second spot. So that's 1 universal out again. Well, B loves C, so therefore there is a Z, LBZ. That's 11 existential in. Just like what we did to 7 to get 9. So we get for all Y, LYB. 12 and 13, arrow out. Everyone loves B, including A. So we get that A loves B. 14, universal out. So we've shown that A loves B. We've shown that A loves everyone. We've shown that everyone loves everyone by universal derivation. Isn't that a fun problem? I thought it's fun. So study that problem because there's a good chance I'll put something, probably not the exact problem, but something very much like that on one of the exams. And keep in mind there are 3 exams for Unit 3, so it's going to show up somewhere. All right, so that's all there is for today's lecture. I'll see you in the next one.